Okay, so now that we've practiced a little bit with decrypting ciphertext when we know that it was encrypted using an affine cipher, let's take a look at kind of another example to see what issues we could potentially encounter when doing this. So here's our situation. We've intercepted this ciphertext and we put it in eCrypt. We happen to know that it was encrypted using an affine cipher. So of course the first thing we did is look at the monograph frequencies. So you can see over here P is the most common and followed by J, S, V, and W. All right. So when we're analyzing this, we know that the most common plain text letters, just kind of in English, are E and T, followed by A is third and O is fourth. So we are, again, just making a guess, but we're guessing that the plain text letter E maps to the ciphertext letter of P, which is the most common letter in our ciphertext, and then that T maps to the ciphertext letter of J, because that's the second most common letter. So from here, we can set up our equations. So remember affine, it looks like f of x equals mx plus a, where the x is the number value corresponding to the plain text letter, and f of x is the number value corresponding to the ciphertext letter. All right, so we need to plug that in. Remember, we're looking for m and a. All right, so we happen to know, just checking our table, that E is equal to 4 and P is equal to 15. So we could plug that in, right? 15 equals M times 4 plus A. And then it happens to be the case that T is 19 and J is 9. So that gives us 9 equals M times 19 plus A. So this is our system of equations that we want to solve mod 26 in order to find the values of M and A. Perhaps you don't really like them written in that way. We could write the same system of equations, just kind of rearranging the terms a little bit so that it looks a little bit more like what we're used to solving, I guess, in algebra. So, of course, m times 4 is the same thing as 4m. So 4m plus a is equal to 15, and then 19m plus a is equal to 9. All right, so what we would want to do is take these two equations and subtract the second one from the first, of course working mod 26. So 4m minus 19m gives us negative 15m, and I'll convert that to mod 26 in just a minute. A minus a gives 0, so that's helpful because it takes away one of our variables or one of our unknowns. And then 15 minus 9 is equal to 6. All right, so it turns out negative 15, you could add 26 to that to get 11m equals 6. And then to solve that, we need to know what is the multiplicative inverse of 11, which turns out is 19. So we multiply both sides of the equation by 19, which would give us m is equal to 6 times 19. And then for that, you probably want to grab a calculator. So 6 times 19 is 114. And then we subtract 26 a bunch of times, and we get m equals 10. All right, so perhaps you're feeling like, yeah, of course that's right, because we're halfway there, we found the multiplicative key. But we have to remember that in the affine cipher, the only allowable values of m are the odd numbers that aren't 13, or in other words, the numbers that don't have a common factor with 26. This is not a valid multiplicative key, so clearly that's not going to help us crack this ciphertext. All right, so what went wrong? Well, we did all the math correctly, so maybe we were wrong in the way that we were guessing which plain text letters corresponded to the most common ciphertext letters. Since we did make a guess on that, it might make sense that, maybe this piece of plain text didn't have E and T as the first and second most common letters. So let's make another guess, right? So let's see. The plain text letter and cipher. So we know that the most common ciphertext letters are P and J. So if it wasn't the case that E was the first most common and T was the second most common, maybe E was the first most common and A was the second most common. Again, this is just a guess. We have to try some things and see what works out. Clearly our first guess did not work out. So if we take these kind of our second guess values and plug them in, remember E is still 4, P is still 15, whoops. A is actually equal to 0, and J is equal to 9 still. So if we make our system of equations this way, we would get 15 equals 4m plus A, so that's the same equation that we had before. And then 9 equals 0m plus A, because the A was 0 again. So this is nice because 0m is actually just, well, 0, so that goes away. And this actually tells us right away from the second equation that the additive key A is equal to 9. Okay, that's cool. So we didn't have to do much work to find that. But now we would still have to plug in that value up into our first equation to be able to solve for m. So what does that give us? That gives us 15 equals 4m plus A, but we're using A is equal to 9. All right, so then we subtract 9 from each side, and we get 4m equals 6. Now, normally at this point, we would multiply by the multiplicative inverse of 4, but unfortunately, 4 does not have a multiplicative inverse. So what can we do instead? Well, we can guess and check. So this was a strategy that I know some of you used when we kind of first started working on modular arithmetic. So we want to know what value of m this is. So I guess there's two ways to think about it. You know the allowable values for m, so you could just kind of start plugging them in and see if any of them satisfy that equation. Or you could start adding 26 to the right-hand side. Oh, sorry, that's the left-hand side, to see what we can solve. So 4m equals 6. We could just add 26 because adding 26 gives it the same value, mod 26. So that would be 32. Whoops. So 4m equals 32, that would give us m equals 8. But again, that's an even number, which we know is not a valid multiplicative key. So let's add 26 again. See what happens. Oops, that's a 26. So 32 plus 26 is 58. 58 is not divisible by 4, so that's not going to work. Let's add 26 again, which would give, I'm going to come over here where I have a little bit more space. 58 plus 26 is 84. 84 is divisible by 4, as it turns out. That gives us m equals 21. So remember, by adding the 26 each time, I'm kind of moving from mod 26 world into regular math world. Basically, I'm trying to find the value of m that is 6 more than a multiple of 26, or in other words, a value so that 4m is equal to 6 mod 26. And it turns out we found m equals 21. So we know 21 is a valid multiplicative key for the affine cipher, since it's an odd number that doesn't have any common factors with 26. So what did we just find? We found additive key 9, multiplicative key is 21. So that's what we would go back and check, whoops, to see if that actually decrypts our ciphertext. And it turns out it does.